Let us now gain an elementary introduction on the scattering of light. Scattering is a phenomena wherein light beam, upon interaction with a particle, which can be both microscopic or macroscopic. That means it could be small as well as large. So light beam interact with this, and rays of light after the scattering is directed every direction. However, before going any deeper, let us take a look at this famous photograph which is known as Earthrise. This basically depicts the rise of Earth as seen from near the moon. This legendary picture, shot on December 24, 1968, during Apollo 8 lunar mission, the first crewed voyage to orbit the moon. In this context, let me mention that during 1960s and early 1970s, NASA had undertaken that the lunar mission, the famous lunar mission, where they actually sent human being on the surface of the moon. That happened when Apollo 11 landed on the moon with two heroes, Neil Armstrong and Edwin Aldrin. However, before that happened, there were a number of Apollo missions where the spaceship traveled very close to the moon and rotated around the moon and obtained valuable information, data which was necessary to send human being on moon. So one such Apollo mission, which is a Apollo 8 lunar mission, that was the first mission that went close to the moon, and it was crewed. So one of the astronauts who was part of this Apollo 8 mission took this famous photograph. This allowed humankind for the first time ever to view the moon sky through the lens of a camera. Acclaimed as the most influential environmental photograph ever taken, this actually holds a wealth of scientific information. Well, let us go a bit deeper and try to decode the science this picture holds. For this picture, the source of light was, of course, the sun, which was hiding behind the lens of the camera, and so not visible here. And the lunar surface in the foreground, and the earth at a distance, are seen basically by the sunlight that reflected off them. So basically, this was diffuse reflection, not specular reflection. Now that you know what is a reflection. But sunlight that traverses through the empty space between the earth, the moon, and also the neighboring places, and in the absence of any matter in this region, there was nothing to return back, to scatter or reflect back the sun to the lens of the camera. And therefore, they appear pitch dark because there was no light, no scatterer, no particle to return the beam of light to the lens of the camera. The earth, and this was the only object which could then return some of the light that landed on them into the camera, and so they could be seen in this picture. The only difference, of course, being that we look at the sky through a layer of atmosphere on our Earth that surrounds while the moon has no atmosphere. You should appreciate the fact that our sky would be just as black as it is in the picture, in this picture, if Earth did not have an atmosphere. Well, let us see what role atmosphere plays in the scattering of sunlight. Atmosphere is a layer of gases called air surrounding the earth that has been retained by gravity. You see the lighter gases like hydrogen, helium, they have escaped because they move with much higher velocity and therefore gravity could not keep them. And as we know, our atmosphere is predominantly made up of nitrogen and oxygen molecules. In 1987, Lord Rayleigh, a British physicist, provided a theoretical description of the scattering of light involving particles smaller than the wavelength of the light. So basically, you have light of wavelength lambda and the particle size of the particle, if I call it A is less than lambda. And Rayleigh had theoretically established that this particle would scatter light uniformly all around it. However, the light with shorter wavelength scatters much more than the light with longer wavelength. In fact, Rayleigh theoretically established this analytical relation that intensity of scattered light is proportional, inversely proportional to the fourth part of the wavelength of the light. All right, now we know that sunlight comprises of multiple colors. Visible, it has this violet, indigo, blue, green, yellow, orange, and red. Violet has the shortest wavelength, and red has the longest wavelength. So now let us do a quick calculation for this scattered intensity, Rayleigh scattered intensity in case of, and compare them in case of shorter wavelength and longer. Let us consider the blue region has a wavelength which is around 400 nanometer, and red roughly has a wavelength which is about 600 nanometer. So the red wavelength, lambda red, is 1.5 times 400 nanometer. 1.5 into 400 nanometer. So this is 1.5 into, this is lambda blue. So then, if we substitute these values here, then IS blue light will be equal to 1 by, let us assume that the proportionality constant is K, lambda to the power, lambda B to the power 4, and I scattering for red light, intensity of scattering for red light will be K by lambda R to the power 4. So ISB by ISR will be equal to lambda R to the power 4 divided by lambda B to the power. Now lambda R equal to 1.5 into lambda b divided by lambda b to the power 4. So this is equal to 1.5 to the power 4. So that means intensity of light, blue light, scattered intensity of blue light is equal to 1.5 to the power 4 into intensity of light, red light, scattered red light. Now 1.5 equal to 3 to the power 2 to the power 4 ISR. So this is equal to 3 to the power 4 by 2 to the power 4. So 3 to the power 4, that means ISB equal to 3 to the power 4 is 81. 2 to the power 4 is 16 into ISR. So that means ISB is nearly 5 times ISR. So blue light will scatter 5 times more than the red light. So with this knowledge, let us now see what happens when white sunlight enters the Earth's atmosphere. So the Earth, this is the layer of atmosphere, and somewhere up is the sun. Light comes here. Before it enters the atmosphere, it is mostly vacuum, so it does not suffer any scattering. There is nothing to scatter light. But as it enters the Earth's atmosphere, oh, by the way, I actually forgot to mention to you that majority of the gas atmosphere is made up of nitrogen and oxygen molecules. And the size of the nitrogen and oxygen molecules is more than even the red light wavelength. So naturally, they will be longer than the wavelength of the shorter than the wavelength of the ultraviolet or blue or green light, etc. So that means nitrogen and oxygen molecules will scatter all the components, all the color components of the white light, because its size is more than the wavelengths of all these. So with this, now let us see what happens as the light enters the Earth's atmosphere. Now as it travels through the atmosphere, nitrogen and oxygen predominantly will scatter light from this white light. Which light will be mostly scattered? Ultraviolet, then indigo, then blue, and decreasing order. However, sunlight doesn't have as much blue as violet or indigo. Blue component is much more than violet and indigo. So violet and indigo will be scattered anyway, but because blue component is much more, so it is the blue which will experience the maximum scattering and red the least. Therefore, if you now look away from the sun and try to see the sky, most likely you will catch blue light. And that is why the sky, our sky look blue. It is the Rayleigh scattering which has made our sky appear blue. And Rayleigh, for his theory, was awarded, I think, 1929 Nobel Prize in Physics. Well, Let us now the moon has no atmosphere. So there is nothing to scatter the sunlight, which is why the entire sky in the Earthrise photo, as we saw, appeared absolutely dark. Here I show you another interesting picture that basically depicts a slice of the blue sky. This is early morning blue sky of Mars. This is basically early morning sunlit Martian sky captured by NASA's InSight lander, which was equipped with a camera that was operated by a robotic arm. During its mission to the red planet in 2009, the bright and blue sky you see here, it is in total contrast to the Earthrise photo. This bears signature of the presence of atmosphere in Mars to scatter sunlight to reach the camera which took this photograph. And the bluish hue of the Martian sky also testifies the invariance of Rayleigh scattering, its universality. It is not only valid in Earth of the planets, it is valid everywhere in the universe. The red color of sun that we see during sunrise or sunset also owes its origin to the phenomena of Rayleigh scattering. The length of atmosphere traversed by sun rays is maximum both at sunrise and sunset, and minimum at midday when the sun is directly overhead. As has been shown in this illustration, this is the position of sunrise, and this is at sunset. And this is the position at the midday where the sun is directly overhead. Now, if you take a look here, you will see that the longest intercept of the sun rays with the atmosphere occurs during sunrise. This is the length of the intercept of the sun ray with the atmosphere during sunrise. This is the length of the intercept during sunset. And this is the length of intercept. You can see that this is shortest and these are the longest. Now, longest intercept means maximum Rayleigh scattering of this white light occurs during sunset and sunrise. Therefore, it actually loses almost all its shorter wavelength component, and probably only a shred of light, red light remains. And therefore, at sunset or sunrise, not only turns incredibly red, but also can be viewed directly by the naked eye. That is because it has lost almost all its intensity, all the colors are gone. So it looks profoundly subdued, and you can actually look at the sun. And because you look directly at the sun, the light that reaches you is red. All other colors are gone because of extensive Rayleigh scattering that has occurred during sunrise and sunset. And during midday, Rayleigh scattering is minimum. So sun light retains lot of intensity. So you never can look directly at the sun. It will be very painful. There is another interesting point that I would like to draw your attention to. You know that on a clear and cloudless bright day, particularly following a shower, the bluish hue of the sky appears much deeper. You can see in this picture, which has been taken following a brief but heavy downpour. And this picture bears testimony to this fact. You can see the captivating blue color of the sky in this picture. So the rain basically cleans up the air by settling down the dust and the other suspended particulates from it, which actually do not contribute to Rayleigh scattering because their size is much longer than the wavelength of the visible light that form the white light that we get from the sun. So if they would not contribute towards Rayleigh scattering, they would only reduce the Rayleigh scattering that otherwise would have taken because they occupy some space and reduces the Rayleigh scattering. So the obvious effect of the presence of these impurities of size far exceeding the light wavelengths in the air is therefore trim the blue of the sky a shade or two, because Rayleigh scattering cannot take place very efficiently because of the presence of them. So sky would look less blue because there has not been too much of scattering of blue light. So if when they settle, Rayleigh scattering becomes much more enhanced and the sky looks blue of the sky is much deeper. Well, we can ask a question here. If Rayleigh scattering makes the sky appear so blue, what is it that makes the cloud floating in the same sky appear so white, milky white? If the cloud looks white, that means the white sunlight gets scattered from the water droplets that cloud is made up of as white alone, preserving all its color. So white sunlight must be scattered from this as white. That's why we see cloud as white. When you look at the sky, the cloud, you see the light that is coming from the cloud. So if the white light gets scattered from the cloud as white only, then only the cloud will appear to us as white. So how come then sky looks blue and the cloud looks white? So what scattering takes place here? Well, in 1908, Gustav Mie, a German physicist, presented a description of scattering of light by particulates of sizes exceeding its wavelength, unlike Rayleigh scattering, where the scattered size was longer than the wavelength of light. Here, the size of the scatterer exceeded that of the wavelength. Qualitatively speaking, the intensity of scattering, known as Mie scattering, which has no restriction on the upper size of the particulate and is invariant of the wavelength of light. So that means in case of the scatterer size is longer than the wavelength of the light. So if I show in the same scale wavelength, so wavelength will be smaller than the size of the particle. So in this case, what this scattering says very qualitatively that it is invariant of the wavelength. So all wavelength will be scattered with equal cross section, starting from violet light and white light, starting from violet to red, all will be scattered equally. And they will be scattered in, again, isotropically, all directions. That means if you have white light, all the components, all the 7 components will be scattered equally. So that means white light will be scattered on white light only. It is not that one light will be scattered less, color will be scattered less than the other. In fact, in Rayleigh scattering, you saw that blue light scatters 5 times more than the red light. So in this case, the white light will be scattered at white light only, and you will see that the color of the cloud is white. So the obvious effect of the presence, so that if you look at the cloud, your eye will catch the white light that is being scattered from there. This thus readily explains that Mie scattering thus readily explains why the presence of particulates in the atmosphere reduces the bluish hue of the sky, or for that matter, why clouds often appear white. Because in case of when raindrops actually settles the suspended particulates of dust, then my scattering cannot take place, because my scattering will scatter the light as white light only. So it will basically reduce the Rayleigh scattering. That means it will reduce the amount of blue light that was being scattered. So sky will appear less blue in the presence of such particles. Let me stop here, and in the next class I'll begin from this point.